the continuum emission from disks, and in particular the millimeter emission from disks. And I will focus on disk masses from the millimeter observations and whether we see hints of this evolution or not, of the evolution of the disk mass from millimeter observations, and the dust structure of classical disks from resolved millimeter observations. Let's see. First, I want to start from where we were yesterday, because from the feedback I realized that the discussion that I presented, what I presented on the different classes of young stellar objects, and and the time scales that you derive from the infrared surveys was a bit confusing. So clearly, I didn't do a very good job in explaining it. So I'll try again in the next couple of slides. I hope you will bear with me, at least those who understood it yesterday, but I think it's important to get everyone on clear things on this. So this is the scheme that I presented yesterday of the evolution of a low mass star. So the formation, the parent molecular cloud and molecular core at the top. This is a prestellar core, is the phase before the formation of a protostar, is observable only in the millimeter, is a cold lump of gas and dust. Okay, then the collapse starts, and you form what we call a protostar. Okay, this is the main accretion phase, so the phase in which you have most of the mass falling into the central disk star system. As we will see tomorrow briefly, I believe this is the stage at which you form the disk. This stage, as shown from this graph here, is not observable still in the infrared. It's still observable only in the submillimeter. The stage in which we start observing the objects in the infrared is the class 1 stage. And here there are a variety of nomenclature, so people may have been confused from what I said. So these were sometimes called infrared protostars, as you see here from this view graph. And some people got confused on whether this was a protostar or not. Let's not stick to the specific of the names. The point here is that the system is being dominated by the disk, and the accretion onto the central star in this particular phase is dominated through disk accretion and not direct in full from the envelope, as in this case. This is the phase that is observable, starts to become observable in the infrared. And then you have the classical phase of disk evolution, which is the phase in which we are mostly interested in, mostly but not exclusively, as we will see possibly at the end of this lecture or tomorrow morning, for the formation of planets, which is the class 2 phase in which you don't have an envelope anymore. The disk, if you want, is isolated from the context. You have a mass reservoir in the disk that is not replenished anymore from the envelope, okay? And you have still accretion onto the disk, but this is fading, and the disk dissipates, forming planets most probably, or other things, okay? And then you have the class 3 systems, which may or may not have a tenuous disk, and may or may not have a planetary system, but they do not have a thick, optically thick, massive disk, like in this case. And in those phases, planet formation is probably over. Okay, so this is, I hope I clarified at least the various phases. And from infrared surveys, you basically probe these 3 phases, okay? And so you get the statistics of sources that are in this phase versus those that are in this phase. And if you have a complete census of the stellar population of a molecular cloud, which is not easy sometimes, you can also get the statistics of the pure photospheres. Okay, the statistics of these do not come from infrared surveys; those come from millimeter surveys, because these are not observable in the millimeter. The ratio of the numbers that I gave yesterday is more or less that you have a factor of 5 to 10 less objects in the class 0 stage than in the class 1 stage, and again, these are a factor of 5 to 10 less than in this class 2 stage, typically in young star-forming regions. And this means that, roughly speaking, the ratio of the evolutionary timescales of these three phases is each a factor of 10, roughly speaking. This is very rough because it assumes a constant star formation rate, which we know is not the case in most cases, okay? Right. Then from the infrared surveys, if you can measure this, the number of objects that are in this phase correctly, and this, as I said yesterday, you have to do either looking at chromospheric activity or proper motion or some other unbiased way that allows you to separate the population of these objects that are associated with the cloud, the foreground and background of stars, which is not trivial in most cases, okay? If you can do this, then from the ratio of these two, you can basically see how many stars you have in any given star-forming region that still have, since these two dominate the numbers, okay? This is a factor of 10 lower. If you don't count, it doesn't matter in this hand-waving sort of counting, okay? But you can put them in if you really want. I mean, it doesn't change the numbers in the end. If you do the ratio of these two and look at how this ratio evolves with time, then you have an indication of how quick is the transition from this phase to this phase, okay, roughly speaking. And this is what is plotted in this type of graph, okay? This type of graph plots the ratio of stars that still have an optically thick disk, so infrared excess, over the total population of the star-forming region, okay? And you basically, this is what is telling you, this graph, is that the inner optically thick disk, okay, so let's say the dust that is close to the star, to some extent, disappears on a time scale, on an e-folding time, that the yellow thing is an exponential fall off, and the e-folding time is, roughly speaking, 3 million years. So it's telling you, roughly speaking, that at the very beginning you have a very high fraction of stars with disks. This means essentially that almost all stars are born with an optically thick disk, almost all of them. You should know that there is always, this doesn't go to 100%, there is always 10-15% in any star-forming regions of objects that do not have a disk, okay? And the reason for this can be many. One of the simplest way of looking at it is that you may have a variety of processes that destroy the disk very early on. So an example is if you have a multiple system forming, multiple system of stars, you can have a dynamical interaction that throws away one of these stars, for example, and may throw it out with a very tiny disk that dissipates very quickly or without a disk. Or if you have a binary system, in this case, disk evolution might be faster than in single stars. And in fact, a large fraction of the stars that have without disk in young star-forming regions are in a closed multiple system. So basically, it's difficult to retain the disk. Okay, or you may even have an extremely fast planet formation process if you can find a way of doing it. The other important thing that this graph says is that, say, 50% of the stars have done what they had to do with their own inner disk by 3 million years. Okay, so either they formed planets or they didn't. But there is a long tail of stars that retain their disk, their optically thick disk, for a very long time. Okay, they are few, but there are a few that survive very long. Okay, how this compares with what I said at the beginning in the first lecture? Can we put some of the things that I said in the solar system in this context? If you look again at the dating of the meteorite, and just to remind you, this is a slice of a meteorite. This is a calcium aluminum inclusion. So these are objects that are little pebbles, okay, between sand and pebbles, so whatever you want to call it, but it's up to 2-3 centimeters in size. These are things like this big. And these are chondrules, smaller than this typically, half a centimeter or so. And the dating, this is the plot from the reference of 2012. So there are less measurements than the one that I showed at the beginning of the week, but the concept is the same. You have the CIAs, so these calcium aluminum rich inclusions that are all born together or formed together, essentially in a very short time scale. And this short time scale is consistent with the time scale of essentially of the length of the time scale between class zeros and class ones, roughly speaking, okay? So these calcium aluminum rich inclusions are consistent, or of course we don't know exactly when the sun was in the class zero phase, okay? So it's difficult to make this link. But the duration of this phase is consistent with the class zero, class one phase. So it's consistent with the period in which there was significant accretion from the envelope onto the disk, okay, and onto the star. The chondrules, on the other hand, evolve on a time scale, form over a time scale that is a few million years, and in fact, the dispersion of the ages of the chondrules is, roughly speaking, 3 million years, which again is consistent with the typical duration of the class 2 phase, as I said yesterday. So the idea, if you want, is that the CIAs are consistent with being formed at the very beginning of the life of the disk, and the chondrules are consistent with being formed throughout the lifetime of the disk during the planet formation phase. Okay. Now, as you've heard from Billy and possibly Phil will discuss also, it's not easy to have objects this big form in the disk, in a gaseous disk, and let it stay there for 3-4 million years, as they have to stay. Okay, this is one of a problem, and we will get to this and observations that constrain the size of the grains and the duration of where the large grains are and for how long they stay in the disk. We will get to this afternoon in the second lecture. Okay. All right, this is to try to put again in context what I said yesterday and trying to clarify things. Let's now go to the thing that I wanted to cover today mostly, and let's start again from where we were yesterday. We will now consider disks, okay? I will focus on the classical disk stage in which you have a star, a flattened distribution of matter around the star, and there is no envelope anymore that is falling onto the disk. If you have a situation like this one, this is the diagram that I showed yesterday. You have a disk that is heated from a central star. There is a range of temperatures. The inner disk is warmer and the outer disk is cooler. You can very well approximate the spectral energy distribution of this system as a superposition of essentially the black body emission at each radii, corrected for the optical depth, obviously. And from this, you can see that there are a few regimes. There is this intermediate regime in which the spectral energy distribution goes as nu to a power that is connected with the temperature radial distribution. And then you have the optically thin part, which is essentially connect with an exponent that is connected with the dust opacity dependent with wavelength. Okay, if you are in the optically thick regime, okay, so if you are here in the near infrared, what you observe as a flux is essentially, well, the usual thing, optically thick emission, the area times the black body radiation at that temperature. When you are in the optically thin regime, so in this area here, what you observe is essentially proportional to the dust opacity, the black body at the temperature that is in that region, and the amount of material that is there in the region, because this dust opacity coefficient is per gram of dust. Okay, so. So basically, if you look in the infrared, you are essentially sensitive to the area that is emitting at that temperature, and if you look in the submillimeter, you are sensitive to the mass that is emitting at that temperature in the outer disk. Okay. I would like to make this digression now, and we will get back to this tomorrow, I think. If you don't have such a nice continuous distribution of dust in the disk, obviously, you may have, for example, a deficit of dust at a certain point. Suppose that you don't have the inner disk for some reason. Then what happens is that the emission at this temperature is suppressed, and so you have a spectral energy distribution that looks like this, okay? And in fact, these are the so-called, there are objects that show this type of spectral energy distribution. These are the so-called transition disks. They are a variety of objects that look very different from one another sometimes, and sometimes look very, very similar. We will get back to this. We think they are related to the evolution of the disks. These are examples of these. So there are, for example, focus on this one, which is the classical transition disk. By the way, I forgot again the reference here. This is from the review of Williams and Chiezza. I'll put the reference again for the slides that you will have online. Basically, the gray, shaded gray area is the median, say, the average spectral energy distribution of a classical disk, okay? Standard Tauri disk with accretion, and it shows a continuous distribution. This is the stellar emission, and this is the cold at mid-infrared to far infrared emission. And as you see, these disks, these transition disks, have a deficit of emission in the near infrared, which means that they miss some hot dust close to the star, okay? And there are a variety of possible differences. There are spectral energy distributions like this one, for example, that are consistent with a gap at a certain distance from the star. So they seem to have warm dust close to the star, then a gap at a certain distance, and then again cooler dust outside. Or there are disks like this one up here, that up there, where I think that we are. Oh yeah, no, it's working again. Where you miss the inner disk, and you have disks like this one, in which you seem to have an homologous decrease of the emission at all the wavelengths. So they are very different. Typically, they account for 10 to 20% of the disk population. So 10 to 20% of the class 2s, not of the entire population, okay? And this means that is a relatively fast phase. So you have 90% of your disk lifetime, 90 to 80% of your disk lifetime in the classical phase, and then 10 to 20% in this phase, and then you are without a disk, essentially, okay? We will go back to this tomorrow, because this may be related to the processes of planet formation or the dissipation of the disk, and I'm sure Phil will discuss them as well. Okay, let's go back to the classical isothermal disks. What can we learn from these spectral energy distributions? As I said, this is connected with the temperature profile. So if you fit these spectral energy distributions with this simple approximation, then essentially you derive a temperature profile in the disk. And this is one of the first things that was done with these with the observations of the disks. This is an example of this type of fits on a set of Tauri disk in Taurus in 1991. And basically what they derived at the time was a distribution of temperatures profiles for the disk that was essentially, roughly speaking, most of the time consistent with, say, roughly between 0.5 and 0.6 as the power law for the temperature profile. If you look at the viscous heating provides a good a poor fit of this, because viscous heating essentially predicts a profile that is consistent with this 0.75 essentially, okay? And the same, by the way, is the profile that you expect for a disk that is not heated internally, is heated externally from the star, but is geometrically thin. Okay, so the irradiation goes down as you go in the outer disk. To explain these temperature profiles with the 0.5, you need to heat up the outer disk essentially. Okay, because the temperature profile is shallower than you expect. And as you already have seen on Monday, this can be done if you have a flare disk, because if you have flare disk, essentially the surface of the disk is increasing more rapidly than as you go away, and so essentially you intercept more radiation than you would by simple dilution. So this was one of the way in which it was fine. You have seen already this picture. This is the simple way in which we picture the disk heating and balance of the cooling. You have a hot surface layer that is absorbing the stellar radiation, roughly speaking, okay? And then this hot surface layer is again re-emitting at longer wavelengths, and half of the radiation is emitted toward the observer or outside the disk, and half of the emission is emitted inside the disk, and is this secondary radiation that is heating essentially the interior of the disk. Okay, so if you have a cut through the disk at a certain radius, and you go from the midplane to the surface of the disk, you have a density profile, as Phil has mentioned, that is Gaussian in the interior, and then perhaps as a power law atmosphere, and then in the temperature profile you have the hot upper layers of the disk that contain a tiny fraction of the mass. Okay, they are tenuous, but they absorb all the stellar radiation essentially. And then you have a fast transition toward the interior temperature, which is essentially contains most of the interior contains most of the mass and is at a lower temperature. Okay, and if you move away from the star, obviously you have less heating from the star, so your temperatures go down, but the overall shape remains the same. Okay, so right. Okay, so these are this is how the temperature profile of the midplane will look like for a flare disk like this one, okay, in which you can absorb the stellar radiation more effectively, because you have essentially increased the flaring in the outer disk with respect to the flat disk. The other thing is that since this transition is relatively sharp, and most of the mass is here, most of the cold mass is here, and the warm atmosphere contains a tiny amount of mass. For the purpose of modeling the disk in the millimeter, what matters essentially is this part of the disk, the midplane, that contains most of the mass and is cold. Okay, so a two-layer approximation, which we normally use, meaning that you have a hot layer that is absorbing the star and a cool layer that is emitting at a cooler temperature, is a good description of the disk at millimeter wavelengths at least. Okay, what happens if you have accretion? If you have accretion, as Phil said, you have an additional source of heating, and this is an example of how important this may be in the disk as a heating. If you go from the inside of the disk to the outside of the disk, so this is the radius in astronomical units, this is the scale height, okay, this is the distance from the midplane, and this is the temperature. If you have a strong accretion, a strong viscous heating, then the inner midplane is heated, and you have this funny profile because the disk is reabsorbing, and you have an intermediate layer that is cooler than the midplane, and is cooler than the surface, which is still heated by the star, obviously. But if you go, as you go outside, this becomes less and less relevant, okay? And in the outer disk, this viscous heating is negligible, in fact. And just to give you an idea of the importance of this at, say, 1 AU, in order to have the temperature in the midplane to be raised, say, at the same level as the temperature of the atmosphere, which is quite a bit of heating, you need to go to mass accretion rates that are of the order of 10 to the minus 7, 10 to the minus 8 solar masses per year, okay? So these are not unreasonably small mass accretion rates, and these are, in fact, the mass accretion rates that you have for the brightest, the most accreting objects in, say, in the T-Tauri phase. So it is actually possible that in the inner disk of the T-Tauris, of the strongest accreting T-Tauris, the internal heating is important, but is important only in the inner disk, not in the outer disk. That is what I will mostly discuss today. Okay, once you have your millimeter measurements, as I said, in the millimeter you observe the optically thin part of the disk. So at 1 millimeter, say, the flux that you observe from your disk star system, let's say, is proportional to the temperature, the Planck function, the dust opacity at 1 millimeter, and the amount of dust. So if you make a strong assumption that you basically decide that you have a typical temperature for this emitting dust, and you assume that you know the opacity, then you can convert directly your observations into a mass of dust. And this is what is typically done. This is mass of dust, so I'm not yet converting into the total disk mass. I'm not yet converting with the gas to dust ratio, okay? If you do this, this is a collection from the review of Williams and Chiezza, so there are now some more observations. I'll show you some other plots of this in a minute, but the general trend is that you have a sort of dependence of this mass of the disk with the mass of the host star, as you see. And basically what you see is that the mass of the disk is of the order of, now this is converted using the gas to dust ratio, is of the order of 1% of the mass of the star, okay? And the other thing that you see are that if you blindly look at what the minimum mass solar nebula requires in terms of total mass, if you look at one solar mass, roughly speaking, half of the stars have more mass, half of the stars have less mass, okay? So it's roughly speaking in the middle. The other thing that you can see in this graph is that in the high mass regime, so beyond 10 solar masses, there are no detections of disks around, or very doubtful detections of disks of around formed already main sequence O stars. Okay. This is most likely because the disk, the massive stars basically photoevaporates the disk very fast, and so even if you have the disk at the formation time, it's lost very quickly. And in fact, there are now ALMA measurements that show that massive protostars do have disks. So there was a long discussion in the past whether these stars form like this one, so they have a disk. And what it seems now the case is that they do form a disk, but the disk is extremely short-lived. Okay, so that's why you don't have it in this diagram. But it's less relevant for planet formation, let's say. On the other side of the spectrum, in the brown dwarf regime, you see that there are mostly upper limit because these were pre-ALMA measurements, and essentially we were lacking the sensitivity to do these measurements. And I'll show you a few measurements in this area later on. Okay. All right. This is a newer version, still pre-ALMA, of that diagram, and this is only for the Taurus molecular cloud. Again, these are unresolved measurements, so these are just photometry of the disk. And basically, what you see from this survey is, again, the problem of the sensitivity that I just alluded to. So when you go into the low mass regime, so we say this is roughly speaking the boundary between stars and brown dwarfs. So for stars, you detect a large fraction of the objects. These are the objects with infrared excess, okay? So we are looking at the detections at millimeter wavelengths of stars that do have an inner disk, okay? That's the thing here. So basically, we are checking the outer disk of these objects. In the solar mass range, we detect most of them. There are upper limits, but they don't dominate the population. In the low mass regime, you are dominated still by upper limits. Okay? If you obviously is less nice than before, looking at the correlation of mass with the mass of the disk with the mass of the star. But nonetheless, you do find, if you do a proper regression, you do find a correlation between the two. Again, we are using this approximation here, okay, for this photon, because we don't know where the dust is so far, okay? We don't know how it's distributed in the disk, so we don't know the detail of the heating at this point. There is also another thing to consider. We are not using here the same temperature for all the disks, because obviously different disks have different stars in the middle, and the heating of the disk, since the heating of the disk is due to the star, it is reasonably obvious that the average temperature of the millimeter dust, the dust emitting millimeter radiation, it depends on the star that you put in the middle and is doing the heating. And in fact, if you look at a set of possible models, you do find that essentially the temperature of the disk is, this is a recent derivation of this, but this has been known from many years, obviously. The average temperature of the region of the disk that is emitting most of the millimeter radiation depends essentially not on the temperature of the central star, but rather on the luminosity of the central star, because essentially you are reprocessing luminosity and you are balancing energies. So what is dominating is the total luminosity rather than the exact temperature of the star, okay? And so this correction factor has been applied here, and the temperatures you see go from, say, 15, 20 Kelvin up to 80 or 100 Kelvin in the most luminous objects. Okay, I'll do the 5-minute pause here. I have two themes as usual that you might be interested in discussing. So the millimeter traces the outer disk mass, as I said, while the near infrared traces the inner disk. Should there be any relation between the two, and which of the two is more interesting? And again, which is connected to the second thing. Mm-hmm. Yeah.
There was this one graph where you showed Q versus, I don't remember what was on the y-axis. And you said that...
I think it's the one that was, I believe, the... this one?
Yes, this
so
one.
That's the frequency.
That's the frequency. And you said typically classical accretion disk theory says Q is around this 0.75.
Yeah.
But
3/4.
3/4, but I remember classical disk theory says that new power law slope in the middle of the Rayleigh curve and the Poynting curve, that should go as nu to the 1/3. And if you go back to
that's what Phil derived at the beginning of the week. So you can check
yes,
on the notes
but
from
I just
that.
wanted to make sure, because there was this other place where you said nu goes as 4Q minus 2 by Q. Now I was just doing a minor calculation, and if you equate this to 1/3, then Q comes to more like 0.54 instead of 0.75, which would place it somewhere here and not there. So yeah.
Well, that depends on the viscosity or the profile of the viscosity. We normally assume we normally assume a constant alpha in this derivation, and that gives you this.
Even so, yes, that's
yes. That's what
That's true, yes. But even taking that into consideration, somehow I remember that that would tell you that new power law slope, the power law, or the power law index there should be 1/3.
Well, we can look at the derivation of the of the viscous heating. Yes,
Okay.
that was what. Yeah. Hi.
In the slide about disk masses,
Yeah.
you wrote that mass of the disk divided by mass of the star is 1%,
Roughly speaking, yeah.
but in the plot
It's
you have a
10%.
log scale. So according to the plot, it looks
Yes.
more like mass of the disk is equal to mass of the star to the power 0.01. Yes, here.
Yeah.
So it looks like power law.
What do you mean power law? So the ratio of the disk mass, the ratio of the disk mass over the ratio, over the star, over the mass of the star is roughly speaking 0.01.
But it's a log scale.
Yeah, both of them are log scale.
Then it's not this, it's power law. It's mass of the disk. is
Well, it
equal
depends
to
how you.
star.
It depends how you. It's even that is a power law, no? It's just a power law of say proportionality. Power law 1.
Well, from the plot, what I conclude is, is that mass of the disk is equal to mass of the star to the power 0.01.
Yeah, no. The ratio at one solar at point 1 you have 1, at 1 you have 10, at 10 you have 100. So the ratio of the two masses is constant, roughly speaking. Yeah,
Oh,
there is a
okay,
factor.
okay,
There is a
fine,
factor,
yes, yes.
but you know.
Oh, yes, okay, fine. I see.
Okay.
And
Yeah.
there is no kind of, because this was observation,
Yeah, that's observations. Yes.
and there is no kind of comparison that has been done between, there is not a model that is predicting that.
That's the problem. There are you need to the collapse models are scale free at the moment unless you do numerical models and they are not yet at a level in which they can predict these kind of things. Okay? So the collapse models, the standard simple theory of collapse is scale free. I mean, you don't. What you end up at the end depends on how much mass you had at the beginning. Okay, so the theoretical predictions are difficult.
Okay,
Yeah. Okay. Yeah. Yes.
Question about this estimation of disk mass. Disk mass is estimated to is a millimeter, sub-millimeter observation.
Yeah.
If when this equation is available, disk have to be optically seen. But
Right.
In sub-millimeter, the inner region is not optically seen.
You're right. You're right. But this region contains a tiny fraction of the mass. Most of the mass is here.
Yeah. But the
So
disk
the-
is very higher.
Yeah, but this is a tiny fraction of the total mass.
Okay.
So the total mass is dominated by this region.
Okay, I see.
And so that's why you have this relationship, because most of the mass is here. Obviously, there is a correction. This is an approximation. There is a correction due to the optically thick inner part, obviously, you're right. But this correction is normally very small. Okay. Okay. All right. So, one of the points that I had here, okay, is well, the first one was the millimeter traces the outer disk mass, the near infrared the inner disk. Should they be related? Okay. Okay. The standard theory relates them because they are connected. Once you form the disk, you have the viscosity that is basically spreading the disk and is accreting. The disk is slowly going down. So the two should be related. One of the questions that I had is that you are deriving the mass of the disk from the dust observations in the outer disk. This is correct, even assuming that this average temperature is a right determination. This is fine for the outer disk, but in the inner disk you are optically thick, so there is some mass that you are losing in the inner disk. This is true, but as we will see, the surface density profiles of these disks are such that most of the mass is actually in the outer disk. So the millimeter emission traces the bulk of the mass of the disk. So there is obviously a small correction if you want to compute exact masses that is due to the inner disk, but it's not dominating the thing. The other thing is that most of the millimeter emission, as you have seen, comes from temperatures of the order of, say, 20, 30 Kelvin around the solar mass star, let's say. And these temperatures are very far in the outer disk. So they are typically in the beyond 40 or 50 astronomical units, which means that most of the mass that we are probing with these photometric observations at millimeter wavelengths is not directly the mass that is taking part in planet formation at 1 to 5 AU, okay? That's a different region of the disk. So obviously, to understand the disk evolution and planet formation, one has to connect all the pieces, okay? And connect from the inner to the outer disk. So that's why it's important, and they should be related. And in fact, tomorrow we will go back to these transition disks and what we can probe at infrared and millimeter wavelengths of the inner part of the disk. Okay. Nonetheless, I mean, you have seen that the plot of Hernandez, the famous fraction of stars with infrared excess. Well, you have it here. The fraction of stars with this is a different version of the same plot. The fraction of stars with infrared excess is going down with time. So an obvious question is the total mass of the disk also going down with time? Okay, this is tracing the inner disk. Actually, this is tracing the very inner disk within less than 0.5 AU, roughly speaking, in most cases. And again, this is interesting, but still is also smaller than where you think planet formation occurs. Okay. One question that is interesting is the total mass of the disk evolving while this inner disk is disappearing? So, in other words, is the mass of the disks that still retain the inner disk here, okay? So the old disks, is this mass smaller than the typical mass of the disks at the beginning or not? Okay, so is this evolution radius dependent? And this is what this graph is trying to address. This is difficult to do because basically you would need samples. Basically what you do is you observe in the millimeter the sample of disks that have infrared excess, so extracted from these samples here. And you try to see whether there is an average decrease in the mass as a function of time. And obviously, this is affected by numerous biases. One of, the most important one is sensitivity bias. The other is the number of objects, which is going down here, the number of objects that have infrared excess. And if you take the Taurus survey that I showed, the plot, this survey here, as a reference, okay, Taurus is a young star-forming region, say, between 60 and 70% of the stars have infrared excess, and this 60-70% of stars with infrared excess have this distribution of disk masses. Okay, so if we take this as a reference and we compare measurements of millimeter emission of disks in other star-forming regions with this one, is this compatible or is different? That's the question that is being addressed here, okay? And To do this, you have to do a complicated analysis because you have to take into account that you have a sensitivity bias, a selection bias. And basically, this plot is a complicated plot, but for each of the star-forming regions that are shown in this plot, Ophiuchus is a young star-forming region, even younger than Taurus, okay? Or more or less the same age. IC348 is here, okay? So it's slightly older than Taurus. The fraction of stars with infrared excess is slightly lower. Upper Scorpius is a very old one with a relatively low fraction of stars with infrared excess. And Sigma Orionis is, your median age star-forming region, where roughly speaking, the disks are exactly at the E-folding time. So roughly speaking, 40% of the disks of the stars have an inner disk. Okay, so there are surveys of all these regions at millimeter wavelengths, and basically what you do in this plot, you draw from the Taurus sample a number of samples that have the same characteristics of your observations in these regions, and you compare the millimeter luminosity of these two, of the random and the real samples, and you extract a probability that these two samples are drawn from the same parent distribution. Okay, and then you plot all these random samples or these probabilities from these random samples in this plot, and you try to see whether your measurements in the various star-forming regions are consistent with the Taurus, with being extracted from the Taurus population or not. Okay, so what you see is that for very young star-forming region, the answer is yes, it's indistinguishable from Taurus. For say IC348 is still indistinguishable. I mean, the probability is still too low to say that this is distinguishable. For Upper Scorpius, it may be close to a 3 sigma distinguishable, okay, but it's not very solid. I'll get back to this in a minute. And from Sigma Orionis, it appears to be significantly different. So this is a bit of a conundrum at this stage, because you would expect if you expect an evolution, a consistent evolution, you would expect Sigma Orionis to be less different than Taurus, than Upper Scorpius, if you want. So let's go in the details for a minute. So the first thing is to go into the details of the ages of this. And we had this discussion on the ages yesterday and the day before yesterday. If you do a dating of the Upper Scorpius, you can do it 2 ways. Again, you can use the pre-main sequence stars, so the young population of not the young population, the low mass population of Upper Scorpius. Okay, they are still in the pre-main sequence evolutionary phase. Excuse me. You do this dating, and you find that this is consistent with an age which is the age that is plotted here, so roughly speaking 5 million years. If you take the more massive stars of Upper Scorpius, they are already on the main sequence, so they are not anymore on the pre-main sequence because they evolve faster. And so you can basically check their main sequence ages using main sequence dating, and it comes into a 10 mega year, roughly speaking, age bin. So whatever you do in this particular case, whether you use the pre-main sequence or the main sequence, they differ as usual, but the object is relatively old, between 5 and 10 million years. And this is consistent again with the fact that a small fraction of the stars of Upper Scorpius have infrared excess, so most of the stars have lost their disk. If you look at Sigma Orionis, Sigma Orionis is a very well-studied cluster for which we have very accurate measurements of the photosphere of many members, And the age distribution, the age spread derive, I mean, the uncertainty in the age, let's put it clearly. The uncertainty in the age derivation is between 3 and 5 mega-years, but the best fitting age is of the order of 3 mega-years. And this is only a pre-main sequence evolution age. But clearly, it seems that is younger than Upper Scorpius, okay? So it seems that this difference is reasonable. Then, I mean, then the second step is, well, perhaps we should look at what we are doing really here. And what we are doing is this one. This is the best that we can do so far. This is a survey of Sigma-Orionis, survey of Sigma-Orionis in the millimeter with the Scuba 2 camera. So it's a fairly large field that contains in total something like 300 objects of Sigma-Orionis, of which, roughly speaking, half of 40%, as we were saying, are class 2s. So roughly 120 objects are with infrared excess in this region. And basically, there are this many detections that you see in yellow here. So essentially there are 5 detections of class 2 objects out of 100, roughly speaking, objects. And there is 1 detection of a class 1 object, 1 detection of a transitional disk, 1 detection of a class 3, which may or may not be misclassified. So that's actually an interesting object to look at. And 3 other detections, which are most likely sub-millimeter galaxies, because we are approaching the sensitivity that we have to worry about background contamination from sub-millimeter galaxies. Okay, so basically this comparison is based essentially on the non-detections, and the statistics of non-detections is telling us that we should be detecting more of these disks if they were the same as the ones in Taurus. Okay. Similarly, in Upper Scorpius, for Upper Scorpius, we now have an ALMA survey, so the sensitivity is much higher than previous observations, and more data is actually coming. But the number of detections is the one that is listed here. So out of 20 disks that have been looked at, roughly speaking, 2/3, between half and 2/3 are detected, and this is the thing. So the conclusion is that the mass difference in this particular case, the mass differences are not seen, but the statistics is not sufficient to really have a strong constraint on the difference between Taurus and this one. Okay, so the conclusion of this so far is that it's not obvious that there is a significant evolution of the outer disk with age. Okay, the total mass, this average number, which is the total mass in the outer disk, as a function of age, for stars that retain the inner disk. So at face value, the conclusion seems to be that when you dissipate the inner disk, very quickly you have to get rid also of the outer disk, okay? But this is something that I think will become much more clear with the new ALMA surveys that we are trying to do now. Okay, the other interesting aspect that I told you I would assess would be to look again at this disk mass versus stellar mass plot, looking at the brown dwarf disks. The reason for looking at brown dwarf disks are several. The first reason is well, to check whether whether the disk masses extend down to that mass range with the same scaling relation, which would connect to the formation process of brown dwarfs, or and the second to check the possibility of forming planets around brown dwarfs, and to study the physical processes of disk evolution in the context of a very extreme case, so not the 1 solar mass star, but the 0.05 solar mass star with a different temperature and so on, different densities and so on and so forth. Okay, in this particular case, I'm showing you first the comparison of the brown dwarfs, so this is just an enlargement of that one. So of the brown dwarfs in Ophiuchus versus the brown dwarfs in Taurus. The one in Taurus are pre-ALMA measurements in this graph, essentially. And you see that most of the upper limits that were in this part are actually, we push down the sensitivity considerably with ALMA. This allows to detect, instead of 1 or 2 brightest disks, detect more than half of the disk. So we detect, roughly speaking, 2/3 of the sample. The other interesting aspect is that we don't have a bias for selecting against bright disks, obviously. Bright disks, we would have detected them easily. Okay? So the fact that the brown dwarf population is contains lower mass disks, essentially disks of lower mass as compared to the mass of the star with respect to the main population, is possibly an indication that disks in the brown dwarf regime are slightly different from the disks in the solar mass regime, and possibly the brown dwarfs may be formed through the dynamical ejection in multiple systems, or at least this becomes a viable possibility for a number of objects. So that's why we don't. That would explain why we don't have high mass disks here. We will get back to the brown dwarf disks again when we discuss the dust evolution this afternoon. The other important point is that so far I have just taken this average value of the temperature and just looked at unresolved images of photometry of disks at millimeter wavelength and derived this rough estimate of the mass in the dust. Obviously, what you would like to do, you would like to figure out how the mass is distributed in the disk, because this is very relevant for the disk models and for understanding also the disk evolution. Unfortunately, this is not trivial. This has not been trivial to do in the past. If you want, for example, to observe 10 AU at 1 millimeter, say, at 140 parsecs, which is Taurus, you need to have 0.14 arc-second resolution, which implies a telescope that is 1.5 kilometer large. So obviously, this cannot be a single telescope. You need to use interferometry. Okay, and that's why ALMA is so important for the study of disks, because ALMA is an interferometer with baselines that will go up to not 1.5, but 15 kilometers, and so we will arrive at 1 AU scale, roughly speaking. Okay. Now I have a small digression, one slide only, not to lose all of you, on interferometry. Okay, so I hope I will go through this in a painless way. So how interferometry works, you have essentially 2 antennas. Every interferometer, I mean, ALMA has 60 antennas, not because an interferometer with 60 antennas works differently than interferometer with 2 antennas, but just because 64 antennas allow you to measure independent 2 antennas interferometers more rapidly. Okay, you have thousands of baselines instead of just 1. Okay, so the concept of interferometry is just 2 antennas or 2 telescopes. You have 2 telescopes separated by a baseline, a source that is far away in the sky, a plane wave that is coming through, a delay which is a geometrical delay in the time of arrival of the signal on the antenna, which is connected to the different path from here to here, plus another delay which is connected to various things that have to go from here to there. And the whole trick of interferometry is just to correct for all these delays, okay? Once you correct for all these delays, you are basically observing with the 2 antennas the same wavefront that is coming. And when you observe the same wavefront, you have all done the Young experiment in the classes, in the early classes of physics. Then you have a fringe pattern, and the spacing and the amplitude of the fringe pattern depends on how well correlated is the source on the sky, so whether it's point-like, whether it's extended, and so forth, okay? So basically, what you measure at the end of this correlation of the signal between the antennas is what we call the visibility function, which is the visibility of the fringes, of the interferometric fringes. And in the baseline space, so the fringe, the visibility depends on the baseline, okay? And the visibility on the baseline space depends on the intensity on the sky, multiplied by this annoying factor, which is the response of your antenna, times this factor. And if you remember your basic mathematics, this is a Fourier transform, okay? So essentially, an interferometer is measuring the Fourier transform of this thing, okay, which is the intensity of the sky convolved with the response of the antenna. So basically, if you have a point source in the sky, the fringes all have amplitude 1, because a point source gives 1 amplitude in the fringes, and so you have constant visibility. All baselines are measuring a constant visibility. If you have a resolved source, an extended source, then your visibility depends on this. And if you have a Gaussian source, a broad Gaussian source, you have a narrow Gaussian source on the visibility plane. If you have a narrow Gaussian source in the sky, you have a broad Gaussian source in the visibility plane. Just to orient yourself. The important thing is that for interferometry, you don't measure this, okay? You measure this. So that's important when you do measurements and observations. You have to realize what you're doing, because otherwise what you derive can be misleading. So one of the things that is important, for example, for interferometry, is that the maximum separations of the antennas give you the smallest angular scale on sky that you can observe, so give you the angular resolution. The closest you can pack two antennas together without crashing them one to another, okay, gives you the smallest separation that you can measure in the UV plane. You cannot put two antennas infinitely close together. This small scale in the UV plane corresponds to a large scale in the image plane, and it means that beyond that scale, you don't see. The interferometer is not sensitive. It's sensitive, sorry. It is sensible, but it's not sensitive. So this means that if you have a star with a disk and a core around it, and you observe it with an interferometer, maybe you see the disk, but you don't see very well the core around it, because the core is extended and you are filtering out. The interferometer acts as a spatial filter, okay? All right, I am too late, but I want to tell one thing first, two things. Well, one thing. Can I tell just this thing? Because it's related to that, and then the results, we'll move it to this. I know, this is the last thing. So basically, when you observe with an interferometer, you have to do a complex thing. So you have to do a model, do a Fourier transform of your model, see what the interferometer could see of that Fourier transform, and then that is essentially what you compare with the model. You compare on the Fourier space, not directly on the image space. This creates a little bit of complication in the way you do it and in the way you show the interferometric data versus the models. So typically you look, for example, at the visibility as a function of distance on the UV plane, and you compare these kind of things. And this afternoon, the results of doing this. Sorry for being late.